Hi, and welcome to this talk, Using Machine Learning and HPC to Accelerate Product Design. My name is Neil Ashton, and I'm a Principal CFD Specialist at AWS. You know, one of the key things is that companies need to design the next generation of a plane, a car, maybe even something like a treatment for a heart disease. What do these things have in common? Well, it's usually that they want to create something more performant. If it's an aircraft, something that can burn maybe less fuel. If it's electric, then something which has further range. Same for cars. You know, it's about driving an efficient, performant design. But one of the key things, of course, is that you want to get it out to the market fast. You want to be able to focus on the innovation and deliver that as quickly as possible. Now, we believe that one of the key ways to do this is through simulation. Whether it's aerodynamics for a plane, whether it's structural, you know, the weight of the plane or the car. For us, we really believe that one of the key things that can help you to innovate faster and bring things to market sooner is using simulation. And the key thing here is that it's not about using physical prototypes. We believe that focusing on simulation can make it faster. But let's take maybe a step backwards and let's think, well, what are the ways that you could design a product, whether it's a car or a plane or anything else? Now, the first one is physical tests. You could build it. You could build a plane, you could build a car, and you could take it to the guys or take it to a track and test it. You know, was your design more performant? But the problem is that's actually quite expensive. It takes time to build the thing. It has to be certified to be able to fly or to go in the car. It has to have a working engine. Where often the time is you want to focus just on a conceptual design. That's something really breakthrough, that the cost and the time to build it is actually a significant portion of the time. Now, let's assume therefore that this is not really a suitable way to do things quickly. So another approach that you can use is things like wind tunnels. Now, the idea here is essentially a test in a lab. It's not out in the real world, it's in an artificial setting. So this, for example, is a great picture. Anybody who's from the Silicon Valley area will probably know this building. It's at NASA Ames. It's a full-size wind tunnel designed to fit actually almost a whole plane inside. But the point here is that it's still a mock-up. It doesn't actually have to be able to fly. The problem is it's obviously still quite expensive because you need to physically make it. There is a time required from an engineer who has an idea to then manufacture and take to one of these facilities. It could take weeks or months to do it. So it's still not fast enough to be able to test designs quickly and give you an insight straight away. This is where simulation comes in. For example, computational fluid dynamics, or it could be finite element analysis for structural. Here, the idea is no manufacture. It's a piece of software. It's a virtual wind tunnel. This means that you can test your designs at a much lower cost and much more quickly than physical testing. But, of course, is it accurate? Now, today is not the time to have a deep dive into the accuracy of these simulation approaches. But one thing that we can say for sure is that the accuracy is quite often linked to the compute. And this is where AWS comes in. Because you need high-performance computing to be able to compute these simulations quickly. For example, if you were to try and do a simulation here of a car, a high-fidelity CFD simulation, something that can give you the accuracy you need to give as good accuracy as physically testing it. It might take 15 days to do this on just several hundred cores. 15 days, it's too long for most companies. If you can actually scale this out, in this example using Amazon EC2 C5N 18x large instances, going out to more than 14,000 cores for a single job, you can get this in 9 hours. Now, of course, for many people in industry, they don't run such high fidelity models. And so from 15 days to 9 hours could be more like several days to less than an hour. That has a meaningful impact because it means that the engineer, the end user, can get their result back super quick and can know whether it was better or worse. But actually, many people are not using the cloud. They're using on-prem at the moment. Actually, what they're seeing is that there's a lot of customer pain points. They're stuck in queues because their high-performance computing resources aren't large enough. Or they've run out of disk space because they're constantly having to delete things. They don't have enough disk space. And the problem is, of course, that this scenario is like the picture on the left. It's a fixed size on-prem HPC resource that you have to fit your jobs in. It could be a fixed size storage as well. Now, what the cloud and AWS have is on the right, where you have the capacity and the agility to be able to run your workload as big as it needs to be, when it needs to be, in a completely agile manner. So if you need one job to run on 5,000 cores, it can spin up to 5,000 cores. But maybe the next day, you don't need to run anything. You only pay for what you use, and you have the ultimate flexibility. This means that you can actually focus on the engineering result and not worrying about, do I have enough hardware? Do I have to go off and buy more hardware? It really means that as an engineer, you can take a simulation approach and get the results when you need to get them. And the sort of things that have enabled this are things like Nitro. The Nitro cards enable you to get all the benefits of the bare metal with the virtualization. We're able to take away what was previously on the CPU offloaded onto a Nitro card, so you get all the performance of the CPU or GPU, and you can let Nitro take care of the rest. This really has a meaningful impact. And for typical CFD codes, like I just showed, the actual difference between bare metal and Nitro is less than 0.5%. Now, one of the things is that we want to make it as easy as possible for you to be able to create these clusters. Yes, you could manually launch some EC2 instances, you could manually connect them together, you could add some storage. But we want to take the pain away, and so that's why we developed AWS Parallel Cluster, that basically takes all that work away from you and allows you, just in a few lines of code, to be able to create a cluster of your choice with whatever configuration you want, with GPUs, with CPUs, and linked to all the storage requirements that you need, such as Amazon FSx for Lustre, all just in a few lines of code. That means, again, as the end user, you can focus on what you need to do, which is to design this new plane or car and not worry about having to provision the hardware or how to set it all up. So let's talk through a few examples. One of the companies that has really taken a lot of benefit from this is Joby Aviation. Now, they're designing an innovative eVTOL, electric vertical takeoff and landing aircraft. Now, the fact that this was such a novel aircraft meant that they didn't actually have a lot of precursor data. And as a startup, they wanted to be able to get new designs quickly. So CFD and simulation was key to them. By using AWS, they were able to conduct thousands of simulations, each on hundreds of cores, using such things as Amazon EC2 C5N, for example, and they're able to use Parallel Cluster to easily deploy the environment. And this meant that they were able to get results, in less than 24 hours that could have taken previously a week. And one of the key things, which we'll talk about later when we talk about ML, is that they didn't have to get rid of data. They could keep every single simulation and just store it in Amazon S3 Glacier in this example. That's very useful if you ever need the data in the future, which we'll get onto. Another example is Boom. So going from an eVTOL to a supersonic plane. And who doesn't love a supersonic plane? I for sure would love to be able to get across from London to Seattle or to the US in a few hours rather than taking a long flight. And they were similar. So they wanted to accelerate the design and construction, and they wanted to be able to get these designs as quickly as possible. And simulation was key for that. They were able to increase their productivity by 6 times versus an on-prem model by using AWS. And they've used more than 53 million compute hours to do this. This is, again, a really good example of where we can take the pain away so you can focus on the simulation and designing the things that you want to bring to the market. Another example now going from the air to the sea is with INEOS, America's Cup team. So they needed to design these amazing boats. In fact, almost flying boats if you saw the way that they are in the water. There's very complicated sails that actually have a lot of structural and fluid simulations to configure exactly how they look and how they move with the air. This meant that they can't just do one simulation. They have to do tens of thousands of simulations to understand how it operates in its design space. By moving to AWS, they were able to do 20 times more than they previously could. And they did this all using Spot, which could help to significantly lower their costs. That's because each of their simulation was actually quite a small simulation, but they had lots of them, so they could really benefit from the spot model. Now, so far what I've spoken about is largely CPU-based approaches. Most of the codes that I mentioned before, and most of the examples, were using things like C5N instances. But what we're seeing is an increased use of GPUs, GPU acceleration. Now, I'm focusing right at the moment around high-performance computing. But what's really interesting is that, of course, machine learning absolutely takes advantage of this. And for us, and for you, the customer, there's no difference in the way that you can deploy this. And Arun, my colleague, is going to go into more detail of this shortly. Now, one of the key things that all customers want is their simulations to come back as quickly as possible. It's never quick enough. And GPU acceleration really gives the ability to do this. But you need things like P4d instances with the latest NVIDIA A100s to be able to do this. You need it connected to the high-speed EFA. You need it to be able to connect to a high-performance storage system. And that's what the EC2 UltraClusters gives you. So let's focus on an example of this. So this was some work that we did with an AWS partner, Xenotech. So they were doing a fully realistic simulation of an aircraft. So a large-scale, 150 million cell, high-fidelity simulation of an aircraft. And what this graph on the right shows you is essentially iterations per minute can be seen as the speed of the simulation, and the bottom being the number of nodes or the GPUs. Now, the yellow line is their previous on-premise result, and you can see that the blue line, the C5N instance, gives better performance both in terms of scale and raw performance than the on-premise HPC cluster. But what's really interesting is the other lines. So we see different GPU instances, and I want you to focus particularly on the darker green and the red. Now, the darker green is the P4d instance with a V100 NVIDIA GPUs, and you can see that offers 1 to 2 times speed up over the CPU-based. But when you move to the latest P4d instances with NVIDIA A100, you're seeing 2 to 3 times faster simulations than the CPU can give you. And for any of the keen observer will see, actually this is already scaling out pretty much as far as the CPU will go, more than 3,000 cores. It won't get any faster, and the GPU gives a considerable speed up. This means as an end user, you can get your results 2 or 3 times faster. Imagine the difference between, let's say, a 24-hour turnaround and a 12-hour. That actually can make a difference from an engineering decision and help you to deliver things faster to market. Now, probably you're seeing this and you're assuming that perhaps this extra speed comes at some cost. Well, actually, you would be wrong because it's actually a lower cost. The amount of compute inside these GPUs means that you can extract more performance for a lower cost. So actually, you're getting it 2 or 3 times faster than the CPU technology at 2 or 3 times lower cost. This is a game changer for the simulation industry, and we're really keen to support this going forward. Now, of course, as I said, one of the key things is that you want to get simulations to come back faster. And GPU acceleration is helping to improve that. But one of the things that most companies are looking towards now is how can machine learning help me to go even faster or to get more insights from the simulations that I've been doing? And to talk about that, I want to introduce my colleague Arun, who's going to talk about how you can innovate even further using machine learning.
Hello, everyone. I'm Arun Subramanian. I lead the high-performance computing and autonomous computing solutions team here at AWS. I'm thrilled to talk about the innovations with machine learning combined with high-performance computing that can have a step change for design and analysis in engineering systems today. So our mission at AWS is to put machine learning in the hands of every single engineer, scientist, and developer out there. The way we do that is through a set of services across the entire stack of machine learning, all the way from the bottom of the stack in providing the best infrastructure to run machine learning, to running machine learning services with SageMaker, to enable developers to both train and deploy models, and produce higher level abstractions of services at the AI level to produce vision, language, and speech, and any number of different services that enable customers to take advantage of AI services quickly. Now today, with the introduction and the fantastic overview that Neil has given, we wanted to give you an overview of what is possible with a class of machine learning called deep learning. And deep learning is unique because of several reasons. One of the main reasons deep learning is unique, and it's taken off and become quite popular in the last close to a decade, is because of its unique ability where if you keep adding more data and increase the model complexity to cope with the data set size increases, then the performance of the models continue to increase. They don't plateau out. Now compare that to traditional machine learning techniques, which have been used for decades in any number of different fields, where if you continue to increase the complexity of the model, or if you continue to add more data set to the model improves only up to a certain point, and then the improvement plateaus off and sometimes actually deteriorates if you add more data sets. With deep learning, the deterioration hasn't really been met yet, and if you continue to add more data sets, and if you add the complexity to the model a little bit to account for the data set increase, you actually continue to see the increase in performance of the model. Now, deep learning has been used quite effectively in many different areas and applications, including autonomous vehicles, and in speech and natural language processing, and even cases where it is the deep learning model has beaten world champions in chess and Go and any number of different places. What we would like to show you today is applications of deep learning that can be applied to deeply scientific endeavors, especially to simulations, and how it can be used to accelerate design, and how we've actually used this to accelerate design in real-world applications. Now, many times when people think about machine learning to augment, say, high-performance computing simulations or using machine learning, they're only thinking about one bucket or one way of using machine learning. What we'd like to highlight here in this slide is there are actually multiple ways in which machine learning, and especially deep learning, can help you accelerate both your design times as well as help you get better insights from the data that you already have. So I would like to think about this in three buckets. The first bucket is shown on the left side, where you already have data either generated from a lot of experimental data like Neil talked about, or a lot of the simulation data that Neil gave a fantastic overview about. But if you have the data, can you actually extract meaningful insights from that data without necessarily going and programming every single thing about that particular data set? That's the first bucket. How do you extract relationships from simulation data or experimental data to then go off and do design analysis quickly or design optimization quickly? The second bucket is where machine learning can actually help accelerate the time it takes to solve high-performance computing simulations. So for example, in CFD, where there is a turbulence model, when you're trying to model turbulence, you can actually augment the way in which turbulence is modeled inside the CFD simulations so that you can speed up the computation so you get the same fidelity as a CFD simulation, but at much smaller timescales. The third bucket is where you don't actually run the original simulation, or you don't rely on the data set that has already been generated. You actually try to formulate the deep learning problem in a way where it learns the solution to the partial differential equations that describe the phenomenon directly. Now here, you don't necessarily need to go in and generate data sets from classical methods and then go in and build what we would call a deep learning model to then predict the outcome that you would get from a CFD simulation, for example. Here you would directly go in and find the solution by sampling the actual equations themselves. Now the advantage of doing this is you can start solving problems that are intractable using traditional techniques. And this is an emerging area of research that's getting quite a lot of attention from researchers and application developers, which will expand the use of machine learning across the board significantly as well. The example we'll be talking about today is in the first bucket, where a lot of data sets have already been generated using CFD. How can we use that to both extract meaningful insights and then use those insights to go do acceleration of our design process? Okay. So the problem statement, and we have a guest speaker from Formula One today who will get into a lot more details about this problem statement. But I'll give you a very quick overview of this one, where if you look at Formula One cars, one of the biggest problems is trying to optimize the flow field behind a particular Formula One car to make sure that the car coming behind a lead car can actually get as close to the lead car as possible to make sure that they can get both maximum performance and the best experience for the fans. Now, to do that, typically you'll have to do many different CFD runs to make sure that the design of the car in the front is optimized to make sure that the car in the back can get as close as possible. Now, the problem statement that we are trying to solve using deep learning is, can we do the same design by reducing the number of simulations it takes without losing the fidelity? The problem statement that's written there is, can we actually determine the flow field behind the lead car using a deep learning model so that we can actually change the characteristics of the lead car a little bit to optimize the flow field behind the lead car, right? Now, the way we went about doing it is actually building a completely new deep learning architecture, which took in the geometry of the lead car and many different types of flow characteristics from the lead car, and use that flow characteristics that was already modeled using CFD and transform the problem from a CFD/numerical regime to an image problem. So once we transform that to an image problem, we feed in all of these different images of geometry and different variables from the CFD simulations like velocity, pressure, that are now described as images into a deep learning model. And the deep learning model then predicts what would be the outcome of the flow field from the lead car as a function of all of the flow characteristics of the lead car as well, that predicts as an outcome, again, images. So as far as the deep learning model is concerned, this is an image-to-image model, which is very well known, and many different types of image-to-image models exist today. But then we had to architect this particular image-to-image model to make sure that we adhere to the particular physics of this particular problem. And this is a deep learning problem that ran on multiple P4d instances, where it's really optimizing the GPU infrastructure to go and maximize the training time. And we can take the models that are trained, which are highly accurate, that we'll have Simon talk about, which can actually reduce the design time by orders of magnitude. So now I'd like to invite Simon from Formula One to take us through their experience of scaling their simulations on AWS.
Formula One's mission is to deliver great racing, and whilst this season is producing a tense championship battle and fierce competition in the midfield, we know it could be even better, and our partnership with AWS is helping us deliver that. Formula One cars are the fastest on the planet and can lap the Silverstone circuit at least a minute faster than the top-of-the-range sports car can. The main reason these lap times are so much faster than road cars, even sports cars, is aerodynamics. But what is aerodynamics, and why does it make a car go faster? Here's a quick example. Imagine you're driving down the motorway with your hand out of the car window. If you hold your hand with your palm facing forwards, you're going to feel your hand being pushed backwards. But if you turn your hand 90 degrees, so your palm faces downwards, the amount of pressure reduces. The amount of pressure you feel will also change as you drive faster or slower. What you're feeling on your hand is an aerodynamic force. In this case, it's a drag force. Here's another example. An airplane wing is shaped in such a way that when air moves over it, it creates a force in the upwards direction. This is a lift force, and it's this lift force that keeps the plane in the air. Now, the aerodynamics of a Formula One car work in the opposite way. These same wing shapes are turned upside down, and now they're making a force acting in the downwards direction, or downforce. But why does downforce make a Formula One car fast? And how does this influence the racing? Now, when a car makes downforce, it is pushed down onto the track. That reduces the chance of the car sliding, and it increases its ability to make grip. This allows the car to corner faster. Now, compared to a sports car, a Formula One car is only 20 to 30k faster on the straights, but it can corner nearly 3 times as fast. The downforce has pushed the car down onto the track, it's stopped its tyres from sliding, and it's allowed it to drive around the corner faster than it ordinarily could. The downside to this aerodynamic performance is something called wake. And here's another simple example. This time, imagine you're facing a sink filled with water, and that water is completely still. Now, if you drag your hand through the water behind your hand becomes churned up and disturbed. The faster you move your hand, the greater that disturbance becomes. Your hand is creating a wake behind it. And even though you couldn't see it, the same would have been happening to the air behind your hand when it was outside of the car window. Likewise, when an F1 car travels through the air, not only is it making downforce that's helping it corner faster, but it's also creating a wake behind it. The faster it goes, or the more downforce it makes, the bigger that wake becomes. The final piece of the puzzle is to understand how this wake influences not the car that makes it, the lead car, but rather the car that has to drive through it, the following car. Current F1 cars are as fast as they've ever been, but what we frequently hear from the drivers is, I can't follow the car in front, or I can't get close enough to overtake. Now, we want fans to see close, exciting racing, but if the cars can't follow each other, if they can't get close enough to overtake, we're not going to be able to deliver the racing that we know our fans want to see. The motorsport division at Formula One was set up to understand why contemporary F1 cars find it so difficult to follow one another and what can be done to improve this. To do this, we primarily use computational fluid dynamics, or CFD. CFD is used to simulate the airflow around and behind the car, and it allows us to see what happens to that airflow when we make changes to the car's shape. When we use CFD to put an F1 car inside the wake of another, what we saw was the following car lost downforce, and as a consequence it went slower, and not just a little bit slower, a lot slower. At 40 metres behind the car in front, the following car had lost around 20% of its aerodynamic performance. At 20 metres, that loss increases to 35%, and at 10 metres, the sort of distance where you need to pull out to overtake, the downforce loss was nearly 50%. The following car had lost nearly half of its aerodynamic performance, and it is this huge loss of downforce that stops the following car getting close to the car in front, and it prevents the wheel-to-wheel racing that we want. Now, clearly this is a big problem, and it gets even bigger. A Formula One team is only interested in the aerodynamics of its own car, a single car in isolation. For this problem, we're interested in the aerodynamics of 2 cars, one car following another. So our CFD simulations needed to be twice as large. Furthermore, given the small size of our research team, we knew from the outset that we would have to use optimization techniques to compensate for the lack of manpower. DOE approaches would allow us to explore more of the design space, but they were also going to increase the computational workload. Clearly, maximising compute resource would make us more effective, and this is why we turned to AWS. Our initial CFD workflow utilised on-premise HPC provided by a third party. The simulations ran on a high-end cluster, but one that was shared with other clients. There were 2 main constraints to this approach. First, we often had to queue behind other customers' workloads. And second, there are limits to the core counts we could run on due to the way the cluster was segregated. This limited our ability to upscale our workloads, and it led to us running single core cases and trying to infer following car performance from just the wake. Our initial brief to AWS was for a solution that would work with our existing CFD vendor's workflow. The solution should allow us to replace all of our single car simulations with following car cases, and despite being larger in size, they should take no longer to solve. Furthermore, we should be able to run significant numbers of these cases in parallel with no queuing. Now, our first cloud workflow was a simple lift and shift migration. This resulted in cases running on 8 instances of C5N 18XL, all managed by AWS Parallel Cluster. The first step achieved that initial goal of allowing us to replace single car cases with a 2-car equivalent. And over time, we've optimized this workflow, and we're now able to run these 2-car cases across 12 instances of C5N, and this gives us a faster turnaround than we previously managed for a single car case. Since that first step, our EC2 usage has evolved to give us even more flexibility in how we manage our HPC workload. We can now switch between lower core counts for cost efficiency, or go the other way and run on much larger 40-instance queues. The larger queues allow us either rapid turnaround of the standard jobs, or the ability to run even higher fidelity transient simulations. These latter cases had previously taken nearly 2 days to solve on premise, but the higher core counts possible on EC2 have allowed us to cut the wall time to just 14 hours. As well as using C5N, we've also added Graviton2 instances to our workflow. Graviton2 can give us an even greater cost efficiency when we want to run large numbers of small jobs in parallel. For these types of workload, moving to Graviton2 has helped us realise up to a 30% cost saving. The range of hardware available on EC2 has allowed us to match the right instance type to the workload. And furthermore, the ability to run across multiple regions and AZs means we can do this at scales that were just not possible with an on-prem solution. This uplift in our compute resource has meant that we can tackle the following car problem far more effectively than before we moved to the cloud. The result of this research is a completely new set of aerodynamic regulations for 2022. These new Formula One cars should be able to race closer than before, whilst retaining the same downforce and thus lap time. So how has EC2 got us here? Well, since the project began, we have run over 7,500 CFD simulations, utilised 16.5 million core hours, and generated over 0.5 petabyte of data. This unprecedented level of research into a new set of regulations has allowed us to slash the loss of downforce previously seen in following. At 10 metres, a following car designed to the new regulations now loses less than 15% of its downforce compared to nearly half previously. And at 20 metres, the downforce loss has almost been eliminated. And we're not finished yet. As Formula One moves into a new era, so will our work with AWS. With the availability of instances such as the P4d, we expect machine learning, deep learning, and AI to push the boundaries of how we run even further. Our research has demonstrated that by changing the way the lead car generates its downforce, we can also change the size and the shape of its wake. But could we have learned those relationships between car and wake quicker? And what else is hidden in the data that we haven't uncovered? By leveraging the data from those 7,500 simulations, it took just 7 hours on a single P4d instance to train a model that has given us an even deeper insight into these car versus wake relationships. This model allows us to describe what we want the wake to look like, and in return it tells us how the flow around the car needs to change to achieve that wake. Tens of thousands of inferences are needed to produce an optimum input, but due to how fast they run, we can ask the model a question and get an optimized answer in around 40 minutes. And we can go further still. By training the models with downforce as the output instead of wake, they now tell us how we need to change the airflow around the car to produce more load. By comparing the results of these new models with the old, we can find areas where the changes align. These are areas where a change will produce both more downforce and make the wake better. Where there is alignment, we can relax the regulations and allow teams more freedom to develop in these areas. Now, any changes that make performance and improve the wake is a good thing. In areas where there is divergence between the two models, in areas where more downforce makes the wake worse, we've got to ensure that regulations remain prescriptive. Essentially, we're using these trained modules to fine-tune the regulations, align our aims with the teams, and thus reinforce the overall objectives. But what about even further into the future? Sustainability is at the forefront of Formula One's plans, and machine learning is driving our ambitions here also. Whereas our research to date has largely been in CFD, F1 teams still rely heavily on physical testing in wind tunnels. A single CFD simulation can accurately describe the performance of a Formula One car at one moment in time. But a single wind tunnel run is able to describe the performance of the car at any point in time around an entire lap. Building the same Aeromap of data within CFD would normally take thousands of simulations and could take days or even weeks to run. But by leveraging machine learning, we can generate the same Aeromap in CFD quicker and more efficiently than before. Using a wind tunnel Aeromap as the training data and those same P4d instances, we've managed to reduce the number of data points required to fully populate Aeromaps by orders of magnitude. We now only need to run tens of simulations instead of hundreds or even thousands to build that complete aerodynamic model of the car. We believe technology like this can be used to replace wind tunnel testing with CFD, but keep compute requirements low. I hope this brief insight into our work at Formula One has shown how EC2 allowed us to shape the regulations behind the 2022 car, and we believe that our partnership with AWS will continue to help shape the sport into the future. Thanks for listening, and happy birthday, EC2.
Thank you, Simon. That was so interesting, and I hope others are inspired by that. You know, that story of starting, as they said, with this lift and shift mentality with high-performance computing. They just wanted to take what they had and then just move it onto AWS, and that's fine. But then what they saw was the ways that they could drive down their costs and improve their performance, which is great to see. I think the really cool thing is that they saw, because they kept all their data, for example, on Amazon S3, they were then able to translate into using machine learning, using the huge data set they had. And the examples they gave of how they have been using machine learning is hopefully an inspiration for others. So I hope you're inspired by this. I hope you can see how machine learning and high-performance computing can really help you to innovate, to design those planes and cars and products faster. And I wish you all the best on your journey to do it. So thank you very much.